Bismillahirrahmanirrahim. Assalamu alaikum students. Last time we discussed the idea of electric potential. We said that electric potential is a scalar corresponding to a vector electric field, right? So if we have some charge, positive charge we have shown Q, we know there is electric field surrounding it. So if we select a point P, r distance from the charge, then the magnitude of electric field at point P is 1 by 4 pi epsilon naught Q by r square. And electric field is radially outward because the source charge is positive. So surrounding this charge, at every point there exists a vector electric field, right? Similarly, surrounding this charge, there also exists at every point a scalar called electric potential. I have given you the expression. If there is point P, r distance from the charge, then the electric potential at point P, V, is given by 1 by 4 pi epsilon naught Q by R, right? In this expression, you must remember that it is assumed that if point P is at infinity, that means if R tends to infinity, then this potential is taken there as 0. So every charge distribution is surrounded by electric field. I mean to say, at every point surrounding a positive or a negative charge or any kind of charge, there exists electric field, which is a vector. Similarly, surrounding any charge distribution, there exists electric potential, which is a scalar. So E is a vector, electric potential is a scalar, right? E is obtained from force, F. V is obtained from potential energy, U, right? So if electric potential is simply a scalar representation of the vector field, right? So we'll continue this topic today. So if V and E are related, there must be some relation. That means if V is given, it must be possible to calculate it. And reverse also. If E is given, we should be able to calculate V from that. So today I will show you how to calculate the potential from the field. So I write calculating the potential from the field. So I mean here calculating the electric potential from the electric field. field is my electric field and potential is electric potential. The basic equation, defining equation which we are going to use and which we have already discussed is VB minus VA is equal to UB minus UA for Q naught. Q naught is a test charge, which in turn is minus WAB by Q naught. Right? Now, I have already explained this expression. Actually, there is some field in certain space produced by some charges. I have not shown them. Now, we talk of 2 points in that field, point A and point B. VA is the electric potential at point A. VB is the electric potential at point B. UB is the electric potential energy of the system when test charge is placed at point A, and UA is the potential energy of the system when test charge is placed at point A, point B. UB when test charge is placed at B. UA potential energy of the system when test charge is placed at point A. Right? Test charge means it is a small positive charge, you know. And when you move test charge from point A to point B, there is a change in the potential energy of the system given by UB minus UA, which in turn is related to WAB, where WAB is the work done by the electric field when we take test charge from A to B. Right? So you move test charge from A to B, electric field does some work, that work is WAB, and this UB minus VA is the corresponding change in potential energy. VB minus VA is the potential difference between the points in, right? So we will use this expression to calculate the potential from the field. So first we take the case of uniform electric field. So first I take if E is uniform, that means throughout the space electric field everywhere is same. Same electric field means that the magnitude and direction both of the electric field at every point is same. You know, the uniform electric field is represented by straight, equally spaced lines of force. So let there be uniform electric field E represented by these lines of force. Electric field is pointing downward, right? So it is uniform. I've shown it by straight lines of force equally spaced. So it's uniform in magnitude and direction everywhere. It will be produced by certain charges. We have not shown those charges which produce it. What we do next, we select 2 points, point A and point B in this field. These 2 points A and B are L distance apart along the field, right? So VA is the electric potential at point A, VB is the electric potential at point B. I want to find VB minus VA. So what I do, I use this relation. I take a test charge, move from point A to point B, and calculate the work done by the electric field on the test charge, substitute that in this relation, and solve for VB minus VA. So it is simple. I show, let me use some other color. Let me use this color. So I show a test charge, positive test charge at one of the positions. I move it from A to B. So this is my displacement vector. I'm taking it towards B, and I take deliberately the straight line path from A to B for making calculation easier. What is the force acting on this test charge when I move it from point A to point B? You know this relation F is equal to QE. What does this say? It says if you have a charge Q, place it in some electric field E, then it experiences electric force given by QE, right? So the magnitude of the force is charge times the field, and the direction of the force is same if the charge is positive, because positive times a vector yields a vector in the positive scalar times a vector yields a vector in the same direction. If my charge is negative, then the direction of the force will be opposed to that of the field, right? So my test charge is positive, it will experience force in the direction of the field. So force experienced by it will be in downward direction. So I show force by another color. So this force experienced by it, whose magnitude is Q naught E. Got it? So what is WAB? You know this expression also, work done by some force if it is constant throughout the displacement is F dot S. That means it will be magnitude of force, magnitude of displacement into cosine of the angle between the vectors. So I can use it here because field is constant and electric force on test charge from point A to point B will stay constant, right? So the angle between displacement and force is 180, cos 180 is minus 1. So it will be simply minus because of cos 180 degree, then force, that is Q naught E, magnitude of force, then the displacement from A to B is overall L. So when I move test charge from point A to point B in this uniform field, the work done by the electric field on the test charge is minus Q naught EL. Let it be my first. So using first in equation, VB minus VA is equal to minus WAB by Q naught. So we substitute for WAB, minus is already there. Then instead of WAB, we write minus Q naught EL, and downstairs we have Q naught. So we got the relation VB minus VA minus V plus minus times minus Q naught will go is EL. This is the relation. So you need to remember that there is uniform electric field and there are 2 points A and B which are separated by L distance along the field. Remember, along the field, this distance is along the field. Then the potential difference between those 2 points is EL. So in this case, point B is at higher potential than point A by amount EL. And from this relation, you can see, we know the SI unit of electric field is, from this relation, the defining equation, it is Newton per Coulomb. From this, it is also volt per meter. But this equation you can use only when I name it A, when the electric field is uniform. So using this equation, if the field is uniform, knowing the field, you can find the potential difference between two given points. We take the next case if E is non-uniform. So second case, if E is non-uniform. So now my pattern of lines of force will be like this. They are curved, so it's non-uniform field. So it is some non-uniform field produced by certain charges which are not shown in the diagram. Again, I select 2 points, point A and point B, right? So electric potential at point A is VA, at point B is VB. Now I move test charge from point A to point B to find the potential difference between the points, and it is not necessary I move the test charge along the straight path. I can move it along some curve like this. At one point I show my test charge Q naught. This is my test charge Q naught. So displacement is along the tangent this way. This it is displacement vector. And you know the electric force on the test charge will be along the field. So it will be somewhat like use another color, somewhat like this. The magnitude of force will be Q naught T, right? Now again, what is WAB? You know when the force is a variable force, then work done is calculated using the definite integral, right? This way, from some I initial position to final position. So we will use this because electric field is non-uniform. That means force experienced by the test charge along its path A to B is non-uniform. It's a variable force. So we have to use the definite integral. That means my WAB is A to B F dot ds. Now what is F? F is force experienced by the test charge, which is Q naught E. I substitute. I take Q naught outside the integral. Then what remains inside is A to B. Inside the integral is E dot ds. So this is my work done. Now using this equation, we write complete equation. Using this equation in VB minus VA is equal to minus WAB by Q naught. Minus is already there. Instead of WAB, we write Q naught A to B E dot ds. Then there is Q naught downstairs. Sorry, there is Q naught downstairs. Here, this will go. So my equation will be VB minus VA is equal to minus A to B E dot ds. Q naught is cancelled out. What remains VB minus VA is minus A dot A to B integral A to B E dot ds. I name it equation B. So this is my equation B. So if the field is non-uniform, then you can use this equation to find the potential difference between the 2 points A and B within the electric field. So you can see this kind of integral is called line integral. Sometimes we state this equation as we say electric potential is the line integral of the electric field. Because this kind of integral is called line integral, you already know that. So if you have to find the potential difference VB minus VA, you need to know the electric field. Put that in this integral and solve for this integral. This is non-uniform case, and uniform case is this. Here one thing is important, L is the distance between the points A and B along the field, right? Now sometimes in this equation, point A and point B both are within the field. Sometimes we take one point at infinity and second point in the field. So if point A is at infinity, right? And VA, we know at infinite distance from the charges, potential is taken as 0, and VA is 0, and point B is some general point P, and point B is some general point P in the field. Then we write electric potential at that particular point P within the field is minus integral infinity to point P E dot ds, right? This is my equation C. I name it C. Only difference between B and C is here both points in case of equation B, point A and point B both are within the field. In case of equation C, point A is at infinity, and there we take potential as 0. And point B we write in terms of general point B within the field. So integration limits change from infinity to point B, and potential at point B is given by this thing, right? Now we calculate electric potential due to some charge distributions. I've already told you that electric field due to a point charge is given by this expression. Today I will show you how to derive it. We derive this expression. I write potential due to a point charge. I show some point charge Q. Now we know the pattern of electric field lines surrounding the charge. It's like this. It is in 3 dimensions actually. This diagram is cross section of that. Electric field is everywhere radially outward, and it decreases as you move away from the charge. So electric field is non-uniform. So we can use this particular equation to calculate the potential difference between 2 points within this field. We select 2 points within this field. This field extends to infinity, so lines will be up to infinity. Let there be point A, RA distance from the charge, RA distance from the charge, and point B, the RB distance from this charge, right? What's the next step? We move test charge from point A to point B. So I take another color. Let me use this color. So I have a test charge Q0. I move it from A to B. This is my displacement vector. Electric field is similarly directed, radially outward. So E and ds are similarly directed, right? We deliberately take point A and B along the radial straight line in order to make calculation easier, but our result will be applicable to all paths connecting point A and point B because electric potential is independent of the path. So we know the force acting on test charge will be similarly directed as E. So VA is potential at point A, VB is potential at point B. So using VB minus VA is equal to minus A to B E dot ds. You can see my displacement is radial. So ds vector is same as dr vector, right? ds is same as dr. And angle between electric field and displacement vector is 0, cos 0 is 1. So it will become VB minus VA is minus A to B. Now A is RA distance from the charge, then it will become RA to RB will just be EDR, right? E dot ds cos 0 is E ds and ds we replace by dr. Point A is RA distance from the charge and point B is RB distance from the charge, right? Now E is what? E is electric field due to the source charge Q at point R distance from the charge. So E is 1 by 4 pi epsilon naught Q by R square. So make the substitution. VB minus VA is minus RA to RB 1 by 4 pi epsilon naught Q by R square dr. So my variable of integration is R. Rest is constant. So I take Q by 4 pi epsilon naught outside the integral. So we'll use another color. So VB minus VA is now minus is there and Q by 4 pi epsilon naught is outside minus Q by 4 pi epsilon naught RA to RB. Then what is there? Dr by R square. Dr by R square. Right? And write it minus Q by 4 pi epsilon naught. I can write it this way. Integral RA to RB R raised by minus 2 dr. You know it is simple integral x raised power n dx is x raised power n plus 1 by n plus 1. So I make use of this form. So what I get, minus q by 4 pi epsilon naught r raised power minus 2 plus 1 by minus 2 plus 1. Then I have to put the limits. Lower limit is ra, upper limit is rb, right? So minus 2 plus 1 downstairs is minus 1. That minus times this minus is plus. So it will become q by 4 pi epsilon naught r is by minus 2 plus 1 is r is by minus 1. That's 1 by r, right? It is simple. And it becomes q by 4 pi epsilon naught. First you write rb instead of r. Then you subtract from that the lower limit value. That is, you replace r by ra. So this is VB minus VA. Let me encircle it. I name this equation first. So if I have 2 points RA and RB, sorry, point A and point B in this field, which I have shown, point charge electric field, this way, then the potential difference between these 2 points is given by this relation. And this is valid for any kind of path. Use it to move the test charge between A and B, even though we have used the straight line path, right? Now see, this gives me the potential difference, not the electric potential at a particular point. We want electric potential at a particular point. So we say let RA tends to infinity and V infinity is taken as 0. So we say let initial point be at infinite distance and that potential at initial point is 0. Then the potential at final point will be what? When RA tends to 0, this will become, when RA tends to infinity, this will become 0. So VA is 0. VB is simply Q by 4 pi epsilon naught RB, right? So VB is 1 by 4 pi epsilon naught Q by RB. Got it? Because RA we said approaching to infinity, this term become 0 and VA is 0. VB will be Q by 4 pi epsilon naught over RB, or in general, V of R, if we are at R distance from the point charge Q, then potential is 1 by 4 pi epsilon naught Q by R. So we have showed how to calculate electric potential due to point charge. This equation I name as second. So you can see that we obtained this particular equation VR is 1 by 4 pi epsilon naught Q by R only when we assumed that at infinite distance from the charge potential is 0. This was one calculation. Then if we have to find the potential due to a collection of point charges, potential due to a collection of point charges, I have already told you that we can make use of the superposition principle. For example, if I have many charges, Q1, Q2, Q3, so on, up to Qn, and we select some point P, and we want to find electric field at point P, let that be V. What we do, we find electric field due to 1 at point P, then due to 2, then due to 3, charge 3 and 4 and so on. But in these calculations, we assume other charges are absent. That means when we calculate potential at point P due to 1, I assume other charges are absent. When I calculate potential at point P due to Q2, I assume others are absent. Then the potential at point P will be simply sum. V1 plus V2 plus V3 plus so on plus Vn, right? Or I can write it in compact form like this. You can write it summation I is equal to 1 to n. If I have n point charges, Vi. Or I can move further because I know V is 1 by 4 pi epsilon naught Q by R. I can write it 1 by 4 pi epsilon naught summation I Qi by Ri, right? When we calculate the electric potential using this idea, we say we are using principle of superposition. Principle of superposition. We say principle of superposition is applicable to electric potential as well, right? It is also applicable to electric field, you know that, but their calculation is a bit complicated because when you add individual electric fields to get the total field, you have to make you have to treat electric field as a vector. You are adding vectors. Here you are adding just numbers. Electric potential is a number, it's a scalar. So you have to simply add it. So it's easier, right? We will do some problems together that will help you to understand. So I name it sample problem. Let it be sample problem 1. It's a simple question. It says what must be the magnitude of an isolated positive point charge for the electric potential at 15 centimeter from the charge to be plus 120 volts. Very easy question. Solution. I repeat the question. What must be the magnitude of an isolated positive point charge for the electric potential at 15 centimeter from the charge to be plus 120 volt? So our unknown is Q, R is given from the charge, and V is also given. So we know electric potential to the point charge is 1 by 4 pi epsilon naught Q by R. We have to solve for Q. So Q is V times 4 pi epsilon naught R. Q is V times 4 pi epsilon naught R. Substitute the values. V is 120 volt plus, then you have 4 pi, then you have epsilon naught. You might be knowing the value of epsilon naught, which is 8.9 into 10 raised by minus 12 in SI units. So it is what? Coulomb square per Newton meter square. Then I have 15 centimeter distance, which I convert to meters, which will become 0.15 meter, right? So I make the calculation, you can check it. It becomes 2 into 10 raised power minus 9 coulomb, which can be written as 2 nano coulomb. This is the solution to simple question. On 20 volt for V, 4 pi epsilon naught value 8.9 10 raised power minus 12 coulomb square per Newton meter square. Then distance is 15 centimeter, which is 0.15 meter. Then you make the calculation 2 into 10 raised power minus 9 coulomb you get, you can check it, which is 2 nano coulomb, because 1 nano coulomb is 10 raised power minus 9 coulomb, right? Then I show you another sample problem, simple problem, sample problem 2. What is the electric potential at the surface of a gold nucleus? The radius is 7 into 10 raised power minus 15 meter, and the atomic number Z is 79. I repeat the question. What is the electric potential at the surface of a gold nucleus? The radius is given 7 into 10 is minus 15 meter, and the atomic number Z is 79. So the nucleus, assumed spherically symmetric, behaves electrically for external points as if it were a point charge located at its center, right? So we treat this golden nucleus as a point charge located at its center, or use the expression V is equal to 1 by 4 pi epsilon naught Q by R. Now Q is the charge of 79 protons. Charge on each proton is 1.6 into 10 to the minus 19 coulomb. So solution is simple. Let me use another color. So V is 1 by 4 pi epsilon naught Q by R. 1 by 4 pi epsilon naught is 9 into 10 raised by 9 Newton meter square per coulomb square. Then I have Q, which is 79 times the charge on proton, which is 1.6 into 10 raised power minus 19 coulomb. Then we have distance from the surface of the gold nucleus to the center, which is 7 into 10 raised power minus 15 meter. So when you solve it, you will get 1.6 into 10 raised power 7 volt, right? This V is for unit, this is for potential. Let me use another color for this. So this is my V, electric potential at the surface of gold nucleus. 1 by 4 pi epsilon naught q by r I have used. This is 9 into 10 is 9 Newton meter square per coulomb square for 1 by 4 pi epsilon naught. It contains 79 protons. Charge on each proton is 1.6 into 10 is power minus 19 coulomb. And 7 into 10 is power minus 15 meter is my R. So potential turns out to be 1.6 into 10 is power 7 volt. 1.6 into 10 is power 7 volt. You check the calculation. Now I will give you some homework. Question. Calculate the potential at point P located at the center of the square of point charges shown in figure 1. Assume that D is equal to 1.3 meter and that the charges are the color Q1 equal to plus 12 nanocoulomb, Q2 minus 24 nanocoulomb, Q3 plus 31 nanocoulomb, Q4 plus 17 nanocoulomb. Figure, let me draw the figure. Figure is like this. This is my Q1. This is my Q2. This is my Q3. This is my Q4. Then this is D. This is D. This is D. And this is D. And the point P is at the center. It is our distance Q3. This is my figure 1. So let me check the figure. Q1, Q2, Q3, Q4. So they are at the vertices of a square D is the side of the square. Calculate the potential at point P. You have to calculate the potential at point P, which is located what? At the center of the square of point charges shown in figure 1. Assume that D is 1.3 meter and that the charges are Q1 is plus 12 nanocoulomb, Q2 is minus 24 nanocoulomb, Q3 is plus 31 nanocoulomb, Q4 is plus 17 nanocoulomb. And you know 1 nanocoulomb is 10 raised power minus 9 coulomb. So do your homework, don't waste your time. That's all for today. And important, don't forget to subscribe my channel. Thank you. God bless you. Assalamu alaikum.